Welcome everybody again to the Scylla Summit. It is an honor for all of us to have you here. As Greg said, I am the VP of Field Engineering at Scylla, an Android it seems. I like to refer to myself as an actual person. I do have needs for leisure, I just ignore them. All right, so as Dor mentioned in his presentation, if we count from the very first time we even thought about Scylla, this year is the fourth year that we have Scylla, that we're doing this. And those past few years, they have been very exciting for big data in general, and for Scylla in particular. Our performance leadership, I think, is solidified at this point. We came to the market with a performance story, and we are seeing the competition slowly understand that our design is superior and adopt it themselves. And don't get me wrong, I want to make this very clear. We will continue to improve it. Our performance will continue to get better. Our latencies will continue to get lower. And you will have many talks in this very summit where you will hear about that. But Scylla is so much more than that. There is more than performance to Scylla. And I was thinking to myself, what could I talk about at the Scylla Summit this year among all of those things that is not performance and would still be exciting? And out of a coincidence, I was just thinking about that, munching on that thought, and one of our enterprise users, Samsung Ads, came to me with an issue on Slack, and this is how they approached this. Hey everyone, long time no chat. Your software works too well. I'll dare to say it's boring. And I was very happy to hear that, but I also thought, okay, great. Among all of the things that Scylla does very well, that's the thing I want to talk to you today about. How boring Scylla can be, how we make that happen, and what we are doing to make it even more boring. I hope it's an exciting talk about a boring database. All right, so before we even talk about that, we need to understand what are the two major kinds of workloads that people run in a database like Scylla. And there are two classes that I want to talk about. The first one is analytics. And when you're running an analytics workloads, you have some characteristics that this workload has. You expect an answer from the database in minutes, maybe hours, in extreme case days. You are talking about terabytes of data that you are moving around, or in some cases petabytes. You are throughput oriented. What matters to you is how long it's going to take to move those terabytes around. And to achieve this, you want to keep your queues full and your parallelism fairly high. You want to use every opportunity to execute a request. On the other side of the aisle, you have real-time OLTP or online, you name it, workloads. They are very, very different from analytics workloads. You expect an answer from the database in microseconds and more commonly milliseconds. You are moving kilobytes of data back and forth to the database. Sometimes you're talking about megabytes, but never much more than that. You are latency oriented. You do care about the throughput, that's why you use Scylla, but you're also very interested in the time it takes for a single request to execute. And to do that properly, to do that with decent latencies, you want to keep your parallelism low to moderate, definitely not as high. And every database specializes in something, and I'm sure it's very exciting to always find like the right tool for the job, the very best. But if you really want a boring infrastructure, you are better off with a single solution. There is no general solution. Everybody specializes in something. So if we had to pick a database to do both, would we pick analytics optimized database to do real-time workload, or would we pick the other way around? And the case I want to make today is that an online database like Scylla is the best framework for you to do this. And to understand why, on a conceptual level, I want to show you what is the role of money and resources in a solution. There are many things in life that money can buy. things like food, clothing, a house where I'm from in Toronto, Canada. It's not that easy, but you can. And throughput. That's especially true in the age of scale-out databases. If you need more throughput, you add more nodes, and you get it. No tricks. But there are things in this world that money cannot buy. This is things like love, happiness, a house in the Bay Area. I don't know how you guys do it, seriously. Maybe you can buy with Bitcoin, I don't know. And latencies. Latencies are a property of the architecture. You can't just get better latencies by adding more stuff. And a great way to understand that, an example on a conceptual level, is how you compare SSD technology with hard drives. You can get any kind of throughput from hard drives just by using more of them, putting them on an array, doing some form of sharding, but when you get to query it, you're always bound by the seek time. So something that delivers latency has to be built for latencies, and Scylla is an example of that. But we don't want to just use the same technology for all of the use cases. That's a great first step, but we want to do more than that, because if you use the same technology but in different clusters, you end up with silos of data, you end up with management issues, your operational costs are going to skyrocket. So you want to run not only the same database, but the same cluster with the same data. But the problem with that is that before Scylla especially, you end up in this tuning game to run a database properly, especially a distributed database. There is a lot of tuning that you need to do. And those workloads couldn't be, as we saw, more different from each other. If you tune something for latencies, you're sacrificing throughput. If you tune something for throughput, you're sacrificing latencies. And on top of that, those patterns are seasonal. Maybe you want to do online during the day when your customers are connected to the database, and you want to do reporting at night, which is an analytics workload, and you're not going to be changing the tuning of the database between one of those operations and the others. It's just not feasible. The classic solution that people have employed for this problem is to use a database like Scylla, or for that matter, Cassandra as well, that supports active multi-data center replication. And what that allows it to do is use the same cluster, have the same data, eventually consistent between the data centers, but the data centers are themselves isolated from each other. So you can have a data center in which you do your analytics using Spark or whichever other tool that you want. And you can have another data center in which you are doing your online workload using Kafka, Akka Streams, or your own application, whatever you want to do. But they are fully isolated from each other. And that works. But literally, it has a cost. And the cost of doing that is that essentially you have to duplicate all your resources. And I'm going to walk you through like a real example with real numbers. Imagine you have 150 terabytes of data. And now you have to replicate that into those two data centers, the analytics data centers and the real-time data center. I'm using as an example, just because the pricing is all online, the i3 Metal instance from AWS that can hold 15 terabytes of data. So the bare minimum that you're going to need is 10 of those boxes. That's going to cost you slightly over $250,000 just on data alone. But now you need to replicate that data in a different data center, and out of a sudden, your cost is now over $500,000. Well, if that's the price you have to pay, I guess that's the price we have to pay. But the problem is, a lot of that is just wasted. And why is that? If you think of your online workloads and the way you run them, you are usually not using all of your resources. You are using the disk storage, yes, but you're not using the full disk bandwidth because you want your latencies to be good. You're not fully utilizing your CPUs for the same reason. So usually you might be using something like 15%, 30% of those resources. I'm trying here to be very conservative, and assuming you are going to be using 60% of your resources to do your real-time workloads. That means that you're not using 40% of your workload to get 40% of your resources to get those great latencies. Analytics, they do tend to use 100% of your resources, but they don't do this for the whole time. You may be doing it at night, and then during the day, you're not really doing anything with that data center. So we're also estimating here that you're going to be wasting 40% of those resources. And what that means is that out of that $500,000, you're wasting $300,000 and over. It's just resources that are there, they are available, but you're not being able to consume it because you're too scared that doing so, trying to put those things together will destroy, if you're lucky, one of your workloads, if you're not lucky, both. And Scylla can help you with that. We are, right now, helping our customers with that. You're going to hear in the summit, I'll mention later, customers that are doing this exact same thing. I mean, don't use 2 data centers, use a single data center, because the database will be able to help you keep those costs in check. We are doing, right now, online workloads, analytics, in the same cluster, in the same data center. And to do that, I'll explain to you briefly, what are we doing when we talk about like tuning and the problem with those workloads influencing each other. You may think that, well, I'm in control of those workloads. It is my analytics. It is my real time. So all I need to do is maybe put a scheduler, put a load balancer, try to restrict parallelism for my application and have separate queues. I'm sure it's a very exciting project to do so. And yes, you can do that between your application, between different parts of your application. But when you run those things, when you put data into the database, that generates background work. That generates work that has to be done in a later stage. And also, example of that, for instance, compactions. You're writing and then you can isolate your writes, all right, but the data that has to be later written to disk and the data that has to be later compacted, you can't really control those things. Turn off your phones. And also, we have maintenance operations, things like repairs. You want to do repairs, and because those operations are so costly, you want to have different schedules and have different ways to do them that might be different between analytics and real time. So those are the real culprits of why it's so hard to do those things at the same time. And Scylla has been solving this problem for a long time. You will hear a lot, if you haven't already, about our schedulers. This is one of the things we are really proud of. We have the I/O scheduler. The I/O scheduler is with us since GA, since our very first version. And what it does is it's going to benchmark your disk. It will figure out what is the correct rate that I can send down to that storage array. And then I will manage all the requests inside Scylla ourselves. We can tag the requests as being compaction requests, as being query requests, as being flushes, repairs, whatever you think. And then the scheduler can say, you're not going to run, you are going to run, and it can then enforce shares between those things. If I say they have the same amount of shares, over time they're going to run for the same amount of time. This has been working great for us. And one of the things we finished this year was the CPU scheduler. The CPU scheduler works very much like the I/O scheduler, with the exception, of course, that it's now arbitraging access to the CPUs. So instead of having a single first-in queue with all your tasks, like compaction, etc., they now all live in different queues. We have a queue for compactions, we have a queue for flushes, we have a queue for your requests, and then I can isolate them. Again, using the same concept of shares. If I have the blue task and the red task, like in this example, you can think that this is probably compaction or writes or whatever you want to imagine. If you give 100 shares to each of those, the CPU scheduler will run one after the other, and then over time, you end up with the same execution time. Now, if I come here and say, no, I want to now change that and say that the red class has 50 shares and the other still has 100, what happens is that now one of the classes runs for twice as much time as the other. And the schedulers are all the time enforcing this, at every millisecond, enforcing this isolation. The second problem is, okay, but how do I find out what is a good number for those shares? Because maybe I can overshoot, or maybe I can undershoot. What we did for that was the Scylla controllers. So the Scylla controllers are dynamic algorithms. The example that I like is like your car cruise control. All that we need to do, all that we need to know as the operator of the controller is what kind of behavior is desirable. So in the example of the car, I want my car to cruise at 60 miles an hour. You don't know all the way in which the components change to make that happen. There is a dynamic algorithm built on a strong mathematical foundation, extensively used in industrial controllers, that we brought to Scylla, we brought to the database world. And again, all the time, every quarter of a second for some controllers, 50 milliseconds for other controllers, they all have their own periods. Those controllers are looking at what's happening in the whole of the database, looking at what's happening with memory, looking at what's happening with the queues, the size of those queues, and deciding, based on those algorithms, how many shares should each class have. And then you don't have to worry about the tuning. You don't have to worry about compactions being too strong. You don't have to worry about them being too weak. And you don't have to worry about, oh, I run one of the workloads at day and the other at night, because the database will automatically adapt to each of those. That allows us to do real-time and analytics in the same data center, in the same cluster, with the same data. Because now, all that is left to do is isolate the actual user workload, the part that we discussed as being feasible. Whatever background operations are generated from that, Scylla will handle. Whatever maintenance tasks are generated throughout the operation of those databases, Scylla will handle. All you need to do is, again, isolate your workload, the parts of the workload, one from another. If you restrict parallelism, if you somehow do some form of load balancing, you will do it. We have a keynote, not a keynote, we have two talks that I would like to highlight from Kiwi.com. They'll be talking about how they're doing this with Scylla right now, at this very moment. Very exciting project to do this, like control analytics. They put a tremendous amount of work on that. And I don't want to spoil their talk, so what I did is that I came up with my own data and did my own testing to show you some data about that. Now, I don't want to have any of the background operations. I want to just show you how you can isolate doing this one workload from the other. So what I did is that I came up with a Scylla node, and I ingested 1.5 terabytes of data. Those are key value, it's essentially key value data with around 4 kilobytes at the payload. And again, I'm not doing anything. I waited for all the compactions to finish. And all I want to do is read from this database that I just restarted. So it's all coming from disk. Those disks are excellent. They are the Samsung Z SSDs. They can do around 10 gigabytes a second in this node that I used. We did 10 gigabytes a second. That very exciting curves that you see there is moving a lot. Those are the latencies that you're already used to with Scylla. Again, the hardware is consistent, everything is consistent, so you do have those very consistent latency lines. Your average latency is slightly below a millisecond. Your P95 is slightly below 2 milliseconds, and your P99 is slightly over 3 milliseconds. Workload doesn't change. I'm reading 200,000 keys per second, and that's it. That's what I'm left with. 0% cache, as I said, hit rate verified in the monitoring to be the case. Now, this is real time. I'm interested in those latencies. I want those latencies to be consistent as I can get them. But I also want to run analytics in parallel with that. That's the whole point of what we're doing here. And then we did. We fire analytics with some random arbitrary parallelism. At first, it was arbitrary. And this is the curve that I end up with. I mean, it's not bad, but it's not what we're hoping for. My average latencies are now slightly below 4 milliseconds. My P95 is around 13 milliseconds. My P99 is 30 milliseconds, roughly. Has some peaks over 60. But the biggest problem with that is that now I am using 100% of the resources. I wasn't, of course, before. Now I am, because I have those two workloads running for this at the same time. And by the way, this is a full table scan, so it reads all of that 1.5 terabyte of data in around 5 minutes. So the whole thing that you see here is zooming into a 5-minute period. We were, as I said, we were actually at bottleneck for this disk, so 10 gigabytes a second. 5 minutes, 1.5 terabyte, pretty good. Biggest problem is that being at 100% resource utilization, both disk and CPU, I can no longer sustain the 200,000 operations a second. So that is actually, looking at the latencies, deceives you a little bit, because you're just looking at the latency curve and say, well, it's not great, but it's not bad either. But you're actually not getting to the throughput that you want. So the real latencies are much worse than that. You no longer see like a flat line. You are now seeing there are times that you cannot do those 200,000 a second. The database will try to compensate later, but you don't have anymore the flat curve that you expect. And again, the way to do this is play a little bit with parallelism. And I spent around 2 days doing exactly that. So you reduce the parallelism, and I reduce it too much, and then the analytics now takes forever. That's also not what I want. I want it to complete on a reasonable time. And then I increased the parallelism a little bit, and then I played with admission control, and I did something outside of Scylla, and I played with it, and after 2 days, that's what I was left with. Now, for comparison, I will show you the numbers. We're doing now 2 millisecond average latencies. We're doing around 5.3 P95 latencies, 14 milliseconds, give or take, for my P99. And the visual comparison gets even more interesting if I show you both at the same time. I'm just speaking the P99 to avoid having multiple lines. As you can see there, after 2 days of fine-tuning this parallelism, I managed to get my online workload, those are just the latencies of the online workload, to have a P99 of around 10 milliseconds. And the original parallelism, 30 milliseconds. Again, I'm talking not about the peaks, I'm talking here about the baseline. The peaks are, as we saw, go higher than that, 60 and etc. I did this by carefully tuning parallelism. And as I said, those were a very exciting couple of days. But that's not what we want. We want to do better. We want to make it more boring. The problem with that is that we invested all this brain power into the controllers because I can derive a relationship between those two things. I can derive a relationship between the background work and between the foreground work with the framework that we used. But I don't know which of those workloads is more important to you. I don't know in which proportion. So I cannot do this. I cannot isolate those things because I don't have that information. Again, I have all the information inside the database to do the isolation between background and foreground because those are queue sizes, those are memory buffer sizes, those are things that are happening. But I cannot get into your mind and ask you and get from there, like, what is the ratio that you would want those workloads to progress at? If I could, this is what I could do. I could use the same scheduler infrastructure that we have. I could use the same fact that the scheduler is at all times guaranteeing isolation between those things, and just add another box in there. Now I have my compaction classes, I have my flush classes, I have my repair classes, I have all of that, but I now put your two workloads in different classes. Now I cannot guess what that number is, but I can get you to tell me. And starting with the next enterprise version of Scylla, that's what we're going to have. The interface itself is subject to change, but most of the code to actually do the isolation is already working. Roughly speaking, as I said, it is the exact syntax is subject to change, but you're going to create a role to which you can assign many users. And you can tell me that you want that role to have 200 shares. For comparison, the default is 1,000, so you know that this is going to be a 5-to-1 relationship. I would give 5 times more importance, in this case, to your analytics workloads. I created the role called analytics just to make it easy. You create whatever you want, you put users into those roles, and you say, give me 200 shares. Now, every query that comes from that will be in a separate class, will be in a separate queue, and they're not going to influence each other that much. And that's what I did. Just visually, before we even can go in and show you, before I'll show you like the numbers, you can already see that this is way more stable. Because I can now overshoot my parallelism. That's what I did. This parallelism here is actually much higher than it was in the first example. I just didn't care about that. I said, guess a number, a high number, put it there. Because the database is now taking care of that for you. And our average latency is as good as the latency I ended up with after all that manual tuning of your user workload, 2 milliseconds. My P99 is actually better than it used to be. And my P95 is better than it used to be, and so is my P99. I am now under 7 milliseconds for the P99 for this workload. Once more, the P99 for the online requests only. The visual comparison, it's even more interesting. Previously, you had the non-isolated full parallelism workload that executes in around 5 minutes. And now you have the same workload with even more parallelism. So I didn't have to do any of that trickery. With a much better latency, with a more stable and consistent latency. But the best part of that is that the time that I spent tuning this was 0. Well, except of course, creating the role and changing the user. But I will not count this as tuning. It's just like okay, create the role. You now connect your application, your full table scan as the analytics role. And there you go. No tuning. 0. That's the best part. The summary of all this is that Scylla is right now already a great choice when you want to do both analytics and real time at the same time, on the same data, on the same cluster, in the same data center. We delivered today a very compelling and flexible solution, and I do invite you to hear more in other talks. But we are improving on this infrastructure. We are reusing the components that we built to make this even better, to make this even more boring. Most of you here know about Scylla. Some of you are users of Scylla. Some of you have experimented with Scylla. You all know that Scylla is fast. And that's true. But performance is yesterday's news. Now it's time to make it boring. Thank you very much. Yep.
Thank you, Glauber. He doesn't want to leave the stage. He's got to get plugged in.
We'll take questions. So I'll have 5 minutes. So.
We have about maybe 2 minutes. So we've got time for a couple of questions if anybody has them.
Over there. You might want to come closer, and Greg will get you the mic. And as a reminder, if you don't get to ask your questions now, we have the box outside. It's not a ballot box, it's a question box. You put your question in there. We'll answer at the end of the conference.
Quick question about the workload for analytics. You mentioned table scan. Can you give a little bit more insight? Did you have any shuffle required in those analytics workload or not?
Can you repeat that last part? Did I have what?
Requirement for shuffle, for instance, if you have an aggregation group by that.
No,
this was just table scan?
This is just a table scan. Like I actually use the code that we have online in our Scylla code examples, the efficient Go full table scan. You essentially divide all of your possible space of data in subtokens, and then you read all of them in parallel, and that's it.
Phil Donahue, for those of you who are old enough to remember that.
So do the controllers keep state for how long? I mean, do they relearn every night that you have a different workload at night? How far back do they look in terms of?
Yeah, so we don't actually use things like machine learning. Maybe we should, and the valuation of Scylla would skyrocket. Even though today the magic word is like blockchain, we should. But it's not. It doesn't really work like that. Like we're not trying to learn a function. So if you're familiar with, it's not really a PID controller, but if you're familiar with control theory, one abstraction that helps you understand more or less how that works is a PID controller. So you only really need to read the state, and then you keep something about, like, in our case, we don't even keep like integral components or anything like that. So we're really only looking at the state of things at the moment. So there isn't really a function to learn. At least in those controllers. We have others that Nadav's going to talk about, like for back pressure and stuff. I don't quite know how those work in detail, but those that I'm talking about here, there's not a lot to learn.